the session. Now I would like to invite K. Harini from 1st BSc Physics to the stage, who will share few words about our speaker Dr. Bhunesh. Sir, shall we start the session? Excuse me. Excuse me, sir.
You're speaking to
Sir,
me?
shall we start the session?
Yes, sure.
Thank you, sir. Now I would like to invite K. Harini from 1st BSc Physics to the stage, who will share few words about our speaker Dr. Bhunesh.
Ladies and gentlemen, Okay, sir. Ladies and gentlemen, it is my distinct honor to introduce Dr. Bhunesh Ramakrishna, an accomplished associate professor in the Department of Physics at the Indian Institute of Technology, IIT Hyderabad. Dr. Bhunesh is a highly respected figure in the field of plasma physics with a special focus on intense laser plasma interactions, photonics, and quantum photonics. His expertise is grounded in his exceptional academic background, including a Ph.D. from Queen's University, Belfast, where he made significant contributions to the study of energetic particles in ultra-intense laser plasma interactions. Over the years, Dr. Bhunesh has made outstanding advancements in cutting-edge research, conducting experiments in some of the world's most prestigious laser facilities. His work ranges from high harmonic generation and ion acceleration to exploring the potential of proton beam therapy for cancer treatment. He has been instrumental in setting up experiments at international laboratories such as Vulcan Petawatt Target Area at Rutherford Lab in the UK, and LED initiatives to install state-of-the-art laser facilities such as the 30 terawatt Taranis laser facility at Queen's University, Belfast. His illustrations career has been marked by numerous accolades, including the Ramanujan Fellowship, the Helmholtz Postdoctoral Fellowship, and the Royal Society Award. He is also an esteemed member of the American Physical Society, the Indian Laser Association, and holds senior membership with IEEE. Please join me in welcoming Dr. Bhunesh Ramakrishna, whose relentless pursuit of scientific excellence and patience for advancing the frontiers of physics continues to inspire and shape the future of research in laser plasma physics and beyond. Thank you.
Thank you, Harini. Education is not the learning of facts, but the training of the mind to think. Now I request our chief guest, Dr. Bhunesh Ramakrishnan, Associate Professor, Department of Physics, IIT Hyderabad, to take over the session. So the session is over to you, sir.
Okay. Thank you. Can you all hear me?
Yes, sir.
Can you all? Yes? Okay. So I'll make the slides to full scale. Okay, good morning everyone, and I'm very sorry that I could not join you directly for this interaction session due to some work here. Today, since your topic is smart generation, next generation nanomaterials for sustainable development of energy and environment. So what I thought was I would like to introduce you to high power lasers, and which this will be used for energy and also for environment. Okay, so we'll have a few details about lasers and their potentials. Initially, what I will be discussing is how this invention of lasers have happened and what are their potentials. And then for the fusion, so this is the concept of inertial confinement fusion with lasers. So what basically we do is we use lasers to produce fusion, and with the help of fusion we'll be able to produce electricity. And there are some experiments in this aspect. If there is time which permits me, then I will show you some of the experiments. Then also we will be using lasers for tabletop accelerations of ions. So basically you know that you might have heard about, since you're all doing some physics and also some interdisciplinary faculty are over there, you might be knowing about these tabletop acceleration of particles. So you might have heard about LHC and all. What we want to do is we want to understand the tabletop acceleration with the help of lasers, which means that we don't need very high energy accelerators, but we can use lasers to produce the acceleration of these particles. And then I will be also showing you some of the experiments which we have been doing. And at the end, what we can try to understand is whether we will be able to create matter from light. For example, can we convert light into matter? So light scattering techniques with the help of lasers. So this is the world map of the ultra-high intense laser capabilities. And in India, we have something around, we have 2-3 places where we have high-power laser facilities. So this is RRCAT, which I have marked in red color, which is having a petawatt laser facility. Okay, so a petawatt laser is nothing but it has 10 to the power of 15 watts. Okay, so you might understand that 10 to the power of 15 watt is so huge, but that is only for a fraction of a second. For example, you might have it for the 20 femtoseconds or 25 femtoseconds. So the power is concentrated so large, but then it can be also the whole grid. I mean, you can say that the power generated at that point of time, 10 to the power of 15 watt or so, is much more the grid of Tamil Nadu or even Telangana or so. But then that is only for a fraction of a second. Okay, I will explain you about all these things in the upcoming slides. So as you can see that there is a large interest of these petawatt lasers all around the world, okay? And in India we have 2 or 3 high power laser systems, and we are trying to understand how we can improve such kind of research in India as well. Yeah, so this field of high intensity laser is barely only 20 years old or 2 decades old, and also we are trying to understand how we can develop this area of research as early as possible in future, so that India will also have a fusion facility with the help of lasers. So the first technique which I would like to show you here is called as chirp pulse amplification. So what is this technique basically is, previously we didn't have lasers of short pulse duration, but to get a short pulse duration laser and also with high power, what we do is we have a short pulse laser. So a laser generally is shown with a Gaussian curve, which means that you have the distribution is Gaussian, which means you will have high power concentrated at one point, and then the wings will have low power. But then as it passes through a pair of gratings, as you all know, gratings are nothing but it will disperse this medium into different colors, and then it will disperse it in such a way so that your 25 femtosecond is made into 1 picosecond or few nanoseconds, and then you will try to, as you know, I mean, you're all doing BSc and MSc, so you might be already knowing about the lasers, how the laser technology has evolved and how the pumping will give you more power, like the population inversion, where you have to have large number of atoms on the higher states. Therefore, what we will do is we will pump these lasers so that it will go for very high energy, and later when the high energy pulse is there, then we will amplify this pulse to shorter pulse duration with the help of opposite pair of gratings. So this technique is very important, and as you can understand that this has got a Nobel Prize in the last, for example, for 2-3 years ago, this technique was given a Nobel Prize, where we were able to understand how we can really shorten the pulse duration of the laser. Otherwise, we will not go for very high powers. If we want to go for very high powers with the help of short pulse duration, then you will be just damaging all these mirrors, and then you will not end up having very high power laser system. So that is why we are trying to stretch the pulse, amplify it to high energies, and then we will have a short pulse resulting, what we will have is a resulting high energy and ultra short pulse. And for this technique, there was a Nobel Prize awarded, and this was discovered in 1985 by Gerard Moreau and also Donna Strickland. Both were awarded Nobel Prize together in 2000 and probably, I don't exactly remember the date, but 3 years before, I think, they have got this Nobel Prize. Okay, so since I have discussed with you the area of this sharp pulse amplification technique. So before this was invented around 1985 or so, the focused power intensities of lasers were not very high enough so that you will be able to do these tabletop acceleration experiments or the fusion experiments. Okay. So the basic idea is to increase the lasers to very high power. Okay, so with the help of this CPA technique, you could go for focused intensities of the order of 10 to the power of 20 watts per centimeter square or so. So when you increase the intensity of this laser, or when you increase the intensity of the light, when you concentrate this, then what happens is you will be able to understand about the bound states of electrons. For example, you want to understand about nuclear physics, you want to understand about ultra-relativistic optics. So when you increase the laser power to higher energies, what you will be doing is you will have a relativistic electrons. So 0.5 MeV is the relativistic energy of the rest mass energy of the electron. Okay, so at this point of time, what will happen is that you will be already seeing the relativistic effects, and as you go on increasing the energy, proton being a bit higher in mass when compared to electrons, so the relativistic effects will kick in only at very high energies of the order of like 1 TeV or so. Okay, so but you can already see the relativistic properties of the electrons when you even accelerate them to MeV or so. So this is very fantastic, and then some nice research can be done where you can see even, you know, when I say here buoyant vacuum, so what you are trying to understand here is you are trying to create matter. Okay, so with the help of light, you will be converting them into electrons and positrons when your intensity is of the order of 10 to the power of 35 watts per centimeter square or so, but for which we need very huge power. The idea here is that whether we could build a miniature sun on the earth. So why we are trying to understand whether we could build a miniature sun on the earth or so, this is mainly because we want to produce fusion. So we can see that sun is able to produce a lot of energy, and it is a continuous form of energy, and there is hydrogen fusion which is happening on the sun, and it's a sustainable fusion which is happening. So whether we will be able to produce such kind of fusion on earth so that we can produce, we can provide a significant carbon-free energy for humankind. Okay. And as soon as, you know, the laser was discovered in 1960 by Theodor Maiman, so initially, then immediately what they thought was that lasers could be used for fusion power. Okay, then there was in the US where they could propose that we will be using lasers for fusion energy, and then there was an enormous lab which is called as Lawrence Livermore National Laboratory, where they started to understand about how we can use lasers for fusion. But the recipe for the fusion which we want to do on Earth is simple. Okay, so hydrogen which we need that is already available from water, and then you filter out D2O. Then you place this recipe in 4 million degree Kelvin oven, which means that you need such very high energy, and that is possible with the help of high energy laser systems. And then what you will try to understand is how you will produce fusion, and then how to use this amounts of clean energy. So the idea is very simple. This is a thermonuclear fusion. You know that in the first picture over here, there are laser beams, and these laser beams or laser produced X-rays would rapidly heat the surface of this deuterium and tritium fuel over here, and it will produce a plasma. And then this fuel which is there, that is compressed, and this compression would lead to very high density, and this high density will lead to very high pressures and temperatures, and the fusion is different, and then fusion ignition is different. So fusion is to combine these lighter atoms together, like hydrogen atoms together, and then that will produce enormous amounts of energy. Now the ignition is a self-sustained fusion. So the ignition happens at 1 million Kelvin or so, and then what happens is this thermonuclear burn which spreads, and then this will be a clean energy fuel with the help of lasers. Okay, and then we are also trying to understand such kind of in our lab as well. In IIT Hyderabad we have not a very high power laser, but we have around 3 to 4 terawatt lasers, and then we will be able to do some experiments at here, and then we will translate the same to high power laser systems in India and abroad. As I was telling you, on much more details of it is that you will have your deuterium and tritium, and then this deuterium and tritium, when you fuse it together, will produce, helium, and then this 14.1 MeV of neutrons, and this 14.1 MeV of neutrons is the one which is mainly essential for the fuel or the fusion drive. Okay, so as you can see here, the fuel pellets which are used for laser fusion, or something like, you might have seen all these ball bearing sized spheres, and these are made up of beryllium, and then you will have a high density carbon over there, and then you will fuse this with the help of laser. But then the problem here is that you might find a lot of problems. I mean, it should be highly symmetric, and then it should be highly uniform when these lasers are going to hit this target. Otherwise, there will be, if there is any irregularity, then that will cause the laser beam to transfer energy to the fuel unevenly, and then there will not be any fusion which happens to the surface of this pellet. Okay, so the basic idea over here is how to use lasers for the fusion, and this is one of the technique. And then here what I am showing you is the National Ignition Facility, and this ignition facility is the world's largest laser which is available, and this is located which is in the Lawrence Livermore National Laboratory, and it covers of the order of roughly 2 football sizes. Okay, and this has something of the order of 8,000 large optical. So you might have seen mirrors, and you might have seen coated mirrors, etc., and maybe you might have seen about 1 inch, 2 inch, and 3 inch. But here you have such huge optics. Even you can have optics of the order of 1 meter in diameter. Okay, so these are very important. So that 1 meter diameter optics is so huge, which means the size of your beam is so big. So you are able to produce such huge beam sizes, and then you are able to concentrate it to micrometer size, and then you will be able to produce high energy density. Okay. So together what you can see on your right side over here is that you have 192 laser beams, and then that delivers the energy. And then so we should understand here that there are two important things. One is fusion and another is ignition. So fusion is something where you can try to concentrate these lighter nuclei and then forms a heavier nuclear, and then there will be a release of energy. But the problem is to have a sustained fusion, which is called as ignition. So which means that if you put 1 class energy, the gain should be 100 class. If you put 1 megajoule of energy, the expected output should be of the order of 100 megajoule. So that is the main area which we are working on how to produce enormous amounts of energy with the help of this kind of laser systems. Okay. And this will produce, and also it is not, when we are able to understand about sun, and this also gives you a fundamental idea about the physics. Not only the application part is physics, but also you can try to understand the fundamental concepts of physics, like how these particles are forming and how this energy is concentrated over this small distances, and how you are able to understand about stars, star formations. Everything could be understood with the help of such kind of facilities. So this is one of the facility which I wanted to show you, and we also have something at RRCAT Indore, which is a DAE facility, and I invite you to see such facilities over there as well. And this is the chamber of target, and you can see that these are two persons who are going inside, and then they are fixing the target and in a lift, and then they will come out, and then these 192, as you can see, there are some holes over here, and that will concentrate, and that will produce the fusion. And there were so many lasers, and also India was also part of some of this effort. And the diff which is there, that was formed to demonstrate a full-scale performance of a 1000 megawatt electricity plant. Okay, so this is one of the applications of very high power lasers, and this is, as you were, your theme of your conference is smart generation materials and also for sustainable environment. So here what we are trying to understand is also to use different kinds of materials. So either we can use on this target which is there, we would like to use some kind of a foam target where you can concentrate energy much, and then the laser energy can be absorbed much better. So we are trying to understand about various different concepts of these materials and how these materials can be used for fusion applications. And this is how all these red colored, this is the chamber, and then you can see that this few fraction of the seconds. Okay, we are not, so then you know that we need to have lasers which works continuously at megahertz or kilohertz laser systems, and then continuously they should be able to give energy to these targets, and then that will be a sustainable fuel power plant. But that research is still going on, and that will take forward for future, maybe in another 20-25 years or so, we will be able to produce laser produced carbon-free energy. Okay, so this is how one of the pellet looks like. This is a gold Hall harem, and this will look something like this, and then you have deuterium and tritium which is there inside this target. And this eye is just to guide you how small this thing. So, and then there is a less than a gram of a fuel, and in future you will be able to produce electricity with the help of a fuel which is 1 gram or so per person per year, and that will solve the so there is a lot of problem for the energy, so we can solve the problem of energy of the humankind. Now the NIF somehow few fusion energy. So they have, and then with the help of 2.5 megajoules of laser energy, which was delivered to the target. So that means that with 2 megajoules, you are able to produce 3 megajoules. So there is some improvement, which means although it is not a 100 cross gain, but still there is a gain. Okay. So this gain would give you several more shots, and then this will produce the ignition. Okay. Now this is something inside the target chamber. Now as I told you before, that this is not only going to understand about various techniques, but here you have supernova explosion. You can also try to understand various parts of physics, for example solar physics, astrophysics. How does the gamma ray burn, how these which are available. So of this laser facility, you will be also able to produce very high pressures, and this high pressures will always produce some kind of diamonds which you can also produce. Okay, and then what are the characteristics of such kind of a setup? Okay, so we will be able to understand about planets, we will be able to understand about the stellar nucleus, and so on and so forth. So this is one of the many applications with the help of these high power lasers, and then you will be able to produce a defining moment, and then you will be able to cater to the energy needs of the bird. Now this is another technique where we were doing some experiments, and this experiment has shown that you will be able to concentrate very high energy laser with the help of a cone kind of a setup, where this is a smart material where you can have a gold, aluminium and gold, and then you will be able to produce a very high density fuel over here with the help of a conical kind of a target. So and then they were able to show that this is possible, and then you will be able to produce, if you have a 1 megajoule of driver energy, you will be able to see a maximum gain of around 200 or 300 or so. But still, people are working on that kind of setup to understand how all these techniques will be formed. And also, you will be able to produce enormous amounts of magnetic field. As you know that when you have these electrons, of relativistic electrons which are flying, so that will produce magnetic fields, and then these magnetic fields will also try to collimate these electron beams. When you have this is a simple your F is equal to Q into E plus V cross B. So when you have large number of electrons which are flowing, that will produce magnetic field, and that magnetic field will also try to produce a force on these electrons, and that magnetic field will have an action on these electrons, and that will have a collimation of this electron beam. So without going into much details of these experiments, I will also try to show you one of the other related activity with the help of high power lasers. That is nothing but replace. So one aspect I showed you is with the help of fusion with lasers, and the other is replacing large accelerators with the help of these lasers. So as you know that you have heard about Large Hadron Collider LHC, and also you have heard about slack linear accelerators and all. So these are very long, 2 miles long, 3 miles long, and for example the LHC is 21 kilometers circular diameter is there. Therefore, it is not always possible to do such kind of experiment if you want to do on a tabletop. So lasers will offer a capability so that you will be able to understand how you can accelerate these mega electron volt or giga electron volt particles on a tabletop. For example, when I say tabletop, it does not mean that it's just on the computer table, but it may be much smaller and much shrinkable size when compared to these accelerators, and also cost wise it will be much cheaper. Okay, so I was discussing about this CPA initially, so I don't want to discuss this again, but why these laser accelerated ions are of interest? Because these laser accelerated ions are of interest because they are of very short pulse duration, the divergence is much less, and also they can produce very high energy at the moment, like 100 to 150 MeV or so, and they have very high brightness, and also they have a very high current, which is it. And you can see onto the right over here, these are the beams which are produced with the help of lasers. Okay. And this is one of the curve which shows that there are various different laser facilities available all around the world, and then we are able to produce such kind of high powered particle acceleration with the help of lasers. Now also we have used one of the targets, since you said that this is a smart next material target, which we have used here is just water spray. So what we did is we have water spray over here, and then we use laser, and then we break these hydrogen and oxygen ions, and then we are able to produce, a nozzle is there, and then a laser is going to hit the target over there, and then that will have a water spray, and then this water spray is interacting with the laser, and that will produce, and the intensity of this laser is of the order of 5 into 10 to the power of 19 watts per centimeter square or so, and that will produce, this was one of the research highlight where we have produced really very highly mono-energetic protons. So these protons can be accelerated with the help of lasers, and this is like a tabletop acceleration setup where you can easily produce 1 or 2 MeV of proton with the help of low power laser systems. Okay, and also we have produced some negative ions with the help of this water spray targets just by interacting with the help of lasers. So what happens here is oxygen is accelerated, and then on the way it will also strip away some of the electrons, and then you will have O minus also accelerated. So you can see that both positive and negative ions can also be accelerated with the help of lasers. So one of the other applications of this is to use these protons for radiography. So you can, like an X-ray radiography, when you go for your treatment, you will have an X-ray radiograph. Similarly, you can have a proton radiograph, but this proton radiograph has its own merits, because this is like an ultra-fast streak camera. You can even see movement of things within femtosecond time scales, because the production of these protons are of the order of femtoseconds, and you will be able to see. So for example, here is the source of these protons, and you have something over here, and which is moving of the order of very fast femtoseconds or picoseconds. Then these protons will really go, and then because of the electric field deflection of these charged particles, you will be able to see what is happening at ultra fast time scales, which is of the order of, the spatial resolution of this is of the order of micrometers, and the temporal resolution is of the order of picoseconds. As you can see over here, a nice typical proton radiograph, which looks like an X-ray radiograph, but the time of this is of the order of a few picoseconds, and you can see nice striations over here, and these striations of the order of microns. Okay, so that will give you an idea about how you can use protons to understand about the fundamental physics. Okay, and these striations are much similar to what you see in the outer corona of the sun. Okay, so you are able to see such kind of things with the help of proton radiography in the lab. So we are able to create such conditions of the sun in the lab, and then you are also able to probe these techniques over here. So that is what I wanted to emphasize over here. Now, one more aspect which I want to briefly let you know is that we have we want to use these laser-driven protons for radiotherapy as well, okay? But the challenges is you need to have an increase in the energy, you need to have highly monochromatic beams, and also you need to have a beam transport. Now, why we want to use laser-driven protons when compared to normal protons is that because of this, the protons will go and directly hit the target, and the damage is much less when compared to X-rays, gamma rays, or electrons, because the protons are much pure, and then they will go and directly hit your cancer cells. Because when the proton is passing through your body, it will not damage much of your healthy part, but it will go and directly hit it because the protons are very directed. It is, you can understand something like a bullet or a gun. So the gun which will go and directly deposits its energy at one single point without damaging the other areas of the part. So proton radiotherapy is an upcoming field, and this is already there in, for example, in Apollo Cancer Center in Chennai. They have developed this proton radiotherapy, which is, I think, nearby IIT Madras. And if you have time, you can go and visit such places over there. And also the high-power lasers will be useful for various things, like you can do for diffractive imaging, you can do for X-ray scattering, you can do for material phases and thermodynamics, and then you can have the X-ray absorption spectroscopy, and so on and so forth. Okay, so there are various physics which you can do with the help of these high-power laser systems. And these, as I told you initially, these laser-generated things can be also used for production of positron, and you can understand about fundamental pair plasma science. You can also do a lot of this can be also a new source of accelerators, and you can also produce, pair plasma jets and so on and so forth. And you can mimic some ideas of your star, sun, and all with the help of these things in the lab. Okay, these are some of the techniques which shows that you can also create positrons with the help of lasers. One of the idea is Beath-Hitler process and Trident processes, which you might have studied in your BSc or MSc, where you can produce for electron-positron pairs. And these are 2-3 methods from which you can produce directly photons to pair production. But you can see that the conversion efficiency is very, very low. But still, it is really important to understand the things, okay? And you can also produce and simulate real events with the help of these pair plasmas. And with this, I would like to conclude the talk, and I would be happy if you have any questions. And thank you for your patience in listening to the talk. I'm happy to take questions, if any.
Thank you, sir. Now we'll have query section where you can ask any questions.
Okay.
Thank you, sir, for your sharing your insights and expertise with us today. Your lecture has been truly insightful.
Okay. Thank you. Thank you so much, and thanks for your patient listening. And I will sign off. Thanks.
Thank you, sir.
Yes.
Now we would like to invite everyone for a quick photo session with our esteemed speaker. Firstly, I request outside participants to assemble near the stage. As we move forward, I like to remind everyone that poster and paper presentation will be held here in Seminar Hall 2. We encourage everyone to stay seated and actively participate in the discussion. And I request all the poster presenting participants to stay in front of their poster. I repeat, I request all the poster presenting participants to stay in front of their posters. Mrs. P. Valarmadi is requested to report at the MC desk. course, those who haven't sent your file can mail it to this mail ID. Begin with the oral presentation. I'll be calling out the participants one by one. When your name is called out, please come forward to present. To start with, first we have Annie to present.
So hydrogen is the smartest molecule. Well, that knows what to do at a given time. A happy morning to one and all present here. Here I am Annie. So today my topic is about synthesis of manganese doped nickel cobalt oxide as a highly efficient electrocatalyst for hydrogen evaluation reaction application under guidance of Dr. P. Balaraju, Coimbatore Institute of Technology, Coimbatore. So before hitting the objective of my work, I would like to say a few words regarding hydrogen. So as we all know, hydrogen is very clean, non-toxic. So the interesting thing about hydrogen is the byproduct of hydrogen fuel is only water vapor. So that proves it's very completely environmental friendly. Next slide. Okay. So as we all know about Tata Motors, so they recently collaborated with Indian Oil Corporation. So they launched India's first fuel cell powered bus called Starbus. So when we talk about Tata Motors, we should not forget about a person who is called as a donor of our world, Ratan Tata. So he contributed so for Tata Motors a very big role, and also he played an important role for uplifting our country towards automobile industry. Next slide. So the objective of my work is to give a highly active earth abundant and a robust catalyst for efficient water catalyst, and also to minimizing the over potential and maximizing the fast charge current, fast charge kinetics, and also to give a unique multi-dimensional morphology, and also to obtain a best results in agriculture and organic farming by using green energy such as hydrogen. Next slide. Okay. As we all know, hydrogen, we have various types of hydrogen production methods. So I would like to mention electrolysis, which I am using. So we can use electric current to split water into hydrogen and oxygen. And also we have various methods like steam methane refining and fermentation. In fermentation, we used to do the biomass is converted into sugar rich. So a sugar rich feedstock, so that can be fermented to produce hydrogen. And also we have high temperature water splitting and photobiological water splitting as well. Okay. I would like to share a few words regarding what is fuel cells. So fuel cells is nothing but it's composed of anode, cathode and an electrolyte membrane. So what happens is in the fuel cells, the stored hydrogen will be passed to the anode of the fuel cell and oxygen to the cathode. So in the anode side, what happens is the cathode will split hydrogen molecule into electrons and protons. So that protons will pass through the porous electrolyte membrane and the electron are forced through the circuit. So that what happen, electric current will generated with excess heat. So at the anode part, the proton, electron and oxygen will combine to produce water molecule. Okay, so this is the experimental procedure for for the preparation of nickel cobalt oxide and manganese doped nickel cobalt oxide with different ratios. So I have used hydrothermal method to prepare nickel cobalt oxide and manganese doped nickel cobalt oxide. In this I have used trimethylamine to give it's a structural directing agent, and it also helps to give a multi-dimensional morphology. Next. So these are the XRD pattern for nickel cobalt oxide and 3 different ratios of nickel cobalt oxide. So in this I get cubic spindle structure with 3D FM and also there is no diffraction peak due to impurities or observed in any of XRD pattern. So next slide. So this is the FE-SEM images of nickel cobalt oxide and Mn doped nickel cobalt oxide. So in this clearly gives that A represents a pure nickel cobalt oxide. It gives nano flake-like structure. When I added dopant as a manganese of 0.01 molarity, it gives nano sheets-like structure, and also for C represents 0.05 molarity ratio of manganese doped nickel cobalt oxide. So it gives flower-like structure, and 0.1 molarity ratio of manganese doped nickel cobalt oxide gives leaf-like structure. So this is the EDAX analysis of the material. So I confirmed my elements by using EDAX analysis, and I also calculated the weight percentage and atomic percentage of each nickel cobalt oxide, and for 3 ratios of nickel cobalt, manganese doped nickel cobalt oxide. Okay. So this is the EDAX images of the material. A represents a pure nickel cobalt oxide, and B, C, D represents 0.01 molarity ratio, 0.05 and 0.01 molarity ratio of manganese doped nickel cobalt oxide. Next slide. So this is a Raman spectra. I have confirmed my material by using Raman peak, and also by using Raman peak I confirmed the elements, what are the elements present in the material. Next slide. So when coming to the application part of my work, I have calculated over potential, Tafel plot, exchange current density and the durability. Next slide. Okay. Electrode fabrication. So when coming to the electrode fabrication, I have used graphite sheet as a working electrode. In that 80% of synthesized material, 1% of PVP and 1%, I mean 10% of carbon, activated carbon. And also by using NMP, I mixed the solution and I coated into 1 cross 1 centimeter of cleansed graphite sheet. So when coming to electrodes, working electrode is synthesized material and reference electrode is AgAgC, which is silver chloride, and counter electrode is platinum wire. So there's a 3 electrode setup which we are using for calculating the calculating over potential and other approaches. So previous slide, can you please? So that's a working electrode and reference electrode and a counter electrode. So this is a LSV curve for pure nickel copper oxide and manganese dope nickel copper oxide for different ratios, which is 0.01 molar and 0.05 and 0.1 molarity ratio. So next slide. So I have calculated the Tafel plot. So by considering LSV and Tafel plot, I have calculated the over potential. So in this, I get a good result in 0.1 molarity ratio of manganese dope nickel copper oxide, which is 189 millivolt at 10 current density. Next slide. So by using cyclic voltammetry, I have calculated electrochemical surface area, which I get good result in manganese dope nickel copper oxide 0.1 molarity ratio. Next slide. So I get good result in manganese in 0.1 molarity ratio, which it have a less charge transfer resistance, so it gives a good efficiency. Next slide. And when coming to durability test, I have tested for 6 hours. The material is stable for 6 hours in the starting point. Next slide. So I am very much interested in organic farming since we have 5 acres of land in our native. So my aim is to give alternative source for diesel and petrol for tractors, wrappers and winders, like fueling the machinery for organic farming. Next slide. So I would like to say we have a fish farming. So we all know in fish waste we have a lot of ammonia. So ammonia is a good source of for every good fertilizer for every plant. So in this hydrogen play an important role. The stored hydrogen can be supplied to ammonia fertilizers, ammonia industry to improve the plants, because since it's very big, it's a good source of nitrogen. So ammonia, so this fish waste contains ammonia and hydrogen can be supplied to ammonia fertilizer industry. This is our fish farming, and we have outlets too. So the water will be given by outlets. The water can be. So, okay, I would like to conclude. By using hydrothermal method, I have prepared manganese nickel copper oxide and manganese dope nickel copper oxide with 3 different ratios, and also I have get lower potential of 187 millivolt of current density and Tafel plot of 225 millivolt decade at 0.1 molarity ratio. And also this work is also focusing on fueling the farm machinery, and hydrogen, as I said before, hydrogen also used in fertilizer industry to produce ammonia. Well, it's a good fertilizer for cultivation because it's a source of nitrogen, and so that it will be very helpful for robust and healthy crops. So next slide. So thank you. Let's make the country green India. Thank you so much.
Thank you, Annie, for your presentation. Next we have Glory Rennie to present.
Good Good afternoon to the dignitaries and all the participants present here. I'm Glory Renita, Ph.D. Research Scholar from Coimbatore Institute of Technology, doing my research under the guidance of Dr. S. Agilan, Professor CIT India. We are working in an Indo-Norwegian collaborative project with Western Norway University of Applied Sciences. My research topic is based on investigation and properties of layered double hydroxide zeolite nanocomposites for their CO2 absorption performance. This is my overview. So as we all know that greenhouse gases are the most heat-trapping gases for our environment, whereas toxic gases like carbon dioxide, carbon monoxide and nitrous gases plays a major role. And here, industries can make use of synthetic adsorbents prepared at a laboratory scale to reduce the emission of carbon dioxide. Also, they are credited with carbon credits. And so in order to ameliorate this problem, we are using synthetic materials, which is zeolites and layered double hydroxide at a laboratory scale we prepare in the lab. They are known to be excellent gas adsorbents and they play a vital role in gas sequestration. So layer double hydroxides, which is LDH, they are nothing but two-dimensional layered nanomaterials. They belong to an anionic clay family. The main prominent feature of this LDH material is that it can standalone form superior with other nanomaterials as well. So the properties of LDHs are, they have a large surface area and they have high positive layer charge. It has a controllable electronic structure. It's recyclable, low cost, less toxic, biocompatible, easy to fabricate, and also easy for synthesis. The other major nano-adsorbent which is used in CO2 adsorption is zeolites. Zeolites are nothing but aluminosilicate members of the family of microporous solids known as molecular sieves. They have a unique honeycomb structure which has numerous pores which can trap CO2 and other gases into its surface. As we all know, there are other materials such as activated carbon, metal organic frameworks in the recent years, but zeolites have caught the recent attention. The main principle of zeolite is that it has the aluminum and sodium ions, which is the aluminum as the minus neutral ions, which is balanced by the sodium plus ions, which has the capacity to absorb CO2 molecules. So this is a schematic representation for the preparation of layer double hydroxide zeolite, magnesium aluminum LDH composite, which has been done through the basic simple hydrothermal method in our lab. And also I have prepared another material which is magnesium cobalt LDH, which was prepared in the same method. So the X-ray diffraction analysis was taken to confirm the structural properties of the material, and the sharp peak confirms the crystalline nature of the material, and also we have calculated the average crystalline size. Here we have tailored the surface morphology and we have studied the morphological analysis through the FESIM, where the A, B and C shows the morphology of magnesium aluminum LDH zeolite, which has its unique cube-like structure with sharp edges, whereas the tailored morphology of magnesium cobalt showed a new type of zeolite structure, which is the soda-like structure with some agglomeration present on the surface of the material, which may be due to the inclusion of LDH dopants. And I've confirmed the elemental composition using the EDAX analysis. And using the FTIR spectroscopy, I have calculated the stretching vibrations, and the prominent vibrations of zeolite are found, which is OSIO and SIO-SI, ALO-SI. And the thermogravimetric analysis was a thermal analysis method which is used to calculate the weight loss of the sample with respect to temperature. And for this particular material, we noticed two weight loss stages, which was found at 300 and 200, which is due to absorbed water in the zeolite, and the peak at DTG curve at 247 degree and 522 is mainly due to the impurities in the LDH material. And here we have confirmed that the magnesium cobalt LDH has a good thermal stability compared to the magnesium aluminum LDH. The bed analysis was taken for the material, which is, when we are talking about zeolite, pore size is very important to trap CO2 molecules into its surface. So we use bed to calculate the pore size, and here the maximum pore volume was found to be 0.02429 centimeter cube per gram, and the pore volume ranged from 5 to 30 nanometers. And the CO2 adsorption analysis was calculated for the material, and here the bed surface area was achieved for around 192.44 meters square per gram, and we have achieved a pore volume of 0.065 cc per gram, and we have achieved a new pore radius, which is a better pore radius compared to the previous LDH, which is 7.913 Armstrong. And for magnesium aluminum aldehyde zeolite, the maximum carbon dioxide uptake was found to be 54.7 cc per gram, which is 2.44 millimoles per gram. So as I said, the prepared composite was prepared and studied, all the characterization was studied. Here, I would like to conclude that the synergistic effect of both the LDH material and the zeolite material shows optimum results in terms of surface area, pore size, adsorption, and compared to the other materials, and also it showed a good crystalline structure and capacity to withstand temperature. Also, the SBET and the pore size proves to be a potent material for the application at large-scale industries which are emitting CO2 precisely. And it was also found that the carbon dioxide uptake was good enough, which is compared to the previous layer double hydroxides and zeolites. So upscaling our research to the next level, we will be using the material at large-scale industries which are emitting carbon dioxide and other noxious gases to estimate the amount of carbon dioxide absorbed. These are the references. I would like to acknowledge, we're grateful to the Research Council of Norway for our financial support and Coimbatore Institute of Technology for academic and laboratory support. Thank you.
Thank you, Glory, for your presentation. Next, we have Mrs. P. Valarmati to present.
Good afternoon, everyone. Myself, Valarmati, Assistant Professor of Physics, coming from Gobi Arts and Science College. So I am going to present my work named as Observation of Induced Symmetric Phases in the HPLC complex derived from the combination of non-mesogenic 1,2 PDA and mesogenic compound 12 OBA. So this slide shows that what I am going to discuss in this presentation. So let's come to the introduction. In the later 18th century, a botanist, Reinster, accidentally discovers the liquid crystal when he was trying to study the carrot root. Naturally, he got an interest in the colorful patterns, and he did his research on the colorful patterns. Finally, he found that the colorful patterns lying between the crystal and the solid, so crystal and the liquid. So he named the colorful pattern as a liquid crystals. In the earliest and middle of 19th century, many researchers and scientists did their work on the liquid crystals and explore many things to the modern world. That is the LC materials, that is the liquid crystalline materials, flow like a liquid, but the arrangement of atoms or molecules in a crystal way. That's why the material is called as the liquid crystals. And they also explore many things like all the organic materials are exposed the liquid crystalline property, but few of the organic materials only shows the liquid crystalline property. We can distinguish the material by the optical properties. So this slide shows the liquid crystals types. There are mainly two types of liquid crystalline. First one is the thermotropic liquid crystals. The thermotropic liquid crystals completely a function of temperature. When we are increasing or decreasing or changing the temperature, we can find the liquid crystalline structures in between the crystal and the crystal and the liquid. Another one is the lyotropic liquid crystal. It is completely depends upon the concentration of a solvent. Okay, so the phases are in between the crystal and the solids, or the smetic and the pneumatic phases. So in between these two phases, there are many different types of colorful patterns we have observed by using POM and DSA analysis. So the smetic phases is less ordered than crystal. That means the liquid smetic phases lying nearly the crystal temperature. Okay, so the arrangement of atoms are like a crystal. Under the smetic phases, liquid crystals have both orientational and positional order. The next one is the pneumatic phases. The pneumatic phases liquid crystals appears nearly the liquid phase. That means the in a high temperature. So it has a lesser order than the smetic phases. So it has the orientational order but have no positional order. So this is the crystal into liquid. When we are applying a temperature to the crystal start to melt and appear the smetic and pneumatic phases and reach the liquid one. So hydrogen bond is a very important phenomena because I have taken one mesogenic and another non-mesogenic compound. In between these two compounds there is a hydrogen bond. Okay, this hydrogen bond only confirms the liquid crystalline nature of the complex. So this is the materials I have used. 1,2 phenylene diacetic acid is a non-mesogenic compound. That means naturally it has no mesogenic properties. But here 4N-2-decyl benzoic acid is the mesogenic compound naturally. It has the mesogenic phases of smetic C and pneumatic naturally. So this is the synthesis. So I have taken 1 mole of both the non-mesogenic as well as mesogenic compounds and dissolved in 7 ml of DMF and allow the solution to stir for 18 hours. Finally, after the 18 hours, I have obtained a white crystalline HPLC complex. So resultant discussion. First, after the obtained white crystalline powder, first we have to find or found is there any hydrogen bond is formed between these two compounds. Okay, so in this FTR spectrum at 3521 cm⁻⁻1 there is a hydrogen bond is making. So from this I have confirmed that the complex is a liquid crystal one. The UV spectrum shows the band gap energy value of the HPLC complex, that is 285 nanometer. 4.3 electron volt. So these two studies are very important to find whether what all the mesophases are lying between these two stage. The POM study shows the pneumatic phases. This one, the first one is the pneumatic mesophases. It is very near to the liquid one. At high temperature, we have observed to 109.03. Okay. So there are many different types of pneumatic phases or the droplets, thread-like. Okay, there are colorful patterns I have observed when cooling pneumatic phases near the liquid at 109.03 degrees centigrade. Okay, after that, while I am gradually decreasing the temperature, I found smetic C. It's this type of structure is called as the broken focal conic structure at 103.57 degrees centigrade. Gradually decreasing the temperature, I found smetic F. Okay, this type of structure is called the checkered board at 85.48 degrees centigrade. Okay, furtherly reduces. Okay, at 81.79 degrees centigrade, I found the smetic G. This pattern is called as the multicolored mosaic structure. Okay, after reducing the temperature, the complex reached the crystal one. Okay, this is the thermal spectrogram readings. Okay, this is the cooling pattern. So at 109, 103, 85, 81, we have observed the pneumatic, SMETIC C, SMETIC F and SMETIC G phases along with the enthalpy values. This is the joule per gram. So conclusion, so the hydrogen bond liquid crystals were successfully synthesized from the non-mesogenic as well as the mesogenic compounds. Okay, the FTIR spectrum confirms the OH bond at 3521 centimeter power minus 1. The optical polarizing optical microscopy studies the what are all the mesophases appears in between these two stages. Okay, DSC thermogram support the observed mesophases from the POM with the enthalpy values. The UV spectroscopy calculates the band gap energy value of 4.3 electron volt, which is applicable for the optoelectronics and display devices. So I would like to acknowledge the UGC, DAC, CSR Kalpakam for funding support, Banariamman Institute of Technology, who is supported the lab facilities, Gobi Arts and Science College, Kobichetipalayam. I am working here. Thank you so much.
Thank you. Next we have Dave.
Good afternoon everyone. I am Devi, Research Scholar from Biotechnology Department, Dr.N.G.P, Arts and Science College. I was born and brought up in Tirupur. At present also I am living in Tirupur. Most of you from this place would know that Tirupur is a textile city. In March 2024, there is a World Survey report which says that there are 10 industries that is polluting the environment. In that, textile industry stands in the 6th place. I am a person living in the textile industry and I used to come across many type of textile waste in my day-to-day life. One such waste is embroidery backing paper. That is the waste, that is the industry that is producing the waste, and after the use, the paper goes to waste or it ends in landfill or it is incinerator. What is embroidery backing paper? How many of you have a t-shirt that has an embroidery design on it? Or a saree that has an embroidery design on it? Or a dress material that has an embroidery design on it? So this is a t-shirt that has an embroidery design on it. So back side of it you can see there is a paper cape. Why is this paper cape? So this is the embroidery machine where your t-shirt is being designed. This machine can design 18 pieces at a time. So what happens, if you see the design, you can see a paper below this. That is this embroidery paper that comes in roll. You can cut in whatever design you want. But what happens is, after your embroidery work is done, these papers will be removed and it ends in landfill. But what is the problem with the paper? Because if one machine can produce 70 to 80 sacks of waste like this, Tirupur has 2,500 to 3,000 machines. So calculate how much sacks of waste will end in landfill or it will be incinerator. So as a science student, I like to give something back to the society. So the objective of the research comes here to recycle this embroidery backing paper waste, to isolate nanocellulose from the waste, to study its yield and to study its physiochemical property, and to check whether this has the efficiency to be used as a reinforcement agent in the production of nanocomposites. So that's with the objective. Going to the methodology, the first step in the methodology is to collect the waste from the industry, clean it and boil it to remove the dirt, dry it in the oven, store it in room temperature for further use. The second step is to remove the hemicellulose. Embroidery backing paper waste is not made from wood pulp, it is made from cotton, and the cotton has cellulose, hemicellulose and lignin. The aim of the project is to isolate cellulose. So we need to remove hemicellulose and lignin. Sodium hydroxide is a classical method to remove hemicellulose. The concentration, temperature and the time for my entire experiment is optimized in the laboratory condition. So after optimal treatment, they were washed and filtered for neutral pH. They were later dried in the oven and wait for the yield calculation. So this is the alkali sample. Next is bleaching step. This step is done to remove lignin. So hydrogen peroxide is the classical method used to remove lignin. Here also the optimal temperature condition, everything has been optimized, and after the treatment condition it is washed and filtered, it is dried in the oven and wait for yield calculation. This bleached sample is taken for acid hydrolysis. The acid I used is concentrated sulfuric acid. Cellulose has two regions, one is amorphous region and the other one is crystalline region. We don't want amorphous region because that doesn't have the crystalline property. The crystalline property lies in the crystalline region because the crystalline property is only necessary for the reinforcement agent. So the amorphous region will be removed by acid treatment. Here also the treatment condition is optimized. So once the treatment is over, it will be stopped by using ice cold water. Later it will be centrifuged to remove the acid. Later it will be dialyzed to remove all the acids and impurities. Later it will be sonicated so that there is no agglomeration. Later it will be lyophilized to remove all the water droplets. So here you obtain a dried powder which you are going to study physiochemical properties and check whether you have nanocellulose extractor. So this is the overall view of acid hydrolysis. So next comes chemical composition. Now I have 4 samples in my hand. One is embroidery backing paper waste, alkali sample, bleached sample and the acid hydrolyzed sample. All the 4 samples chemical composition analysis will be done. This test, the methodology I used is Goring and Mansell's methodology. I have given the pictorial representation. So using this methodology we can calculate how much cellulose, hemicellulose, lignin is present in your sample. Next is characterization study. All the 4 samples were subjected to characterization study and the characterization was studied in Ph.D. I-Tech lab. So this is the overall methodology. So my waste was collected, it was sorted in lab, it was alkalized, it was bleached and it was hydrolyzed. Now all the 4 samples were subjected to these studies. So coming to result and discussion, if you see this, if you see here in embroidery backing paper waste, this was the amount of cellulose, hemicellulose, lignin and ash. After the treatment, if you see, there was 94% of cellulose and the percent of hemicellulose and lignin was reduced. This confirms my treatment was very effective in isolating the cellulose. This is the image of SEM. In SEM also the 4 samples were taken picture and isolated nanocellulose confirmed the presence of spear-shaped nanocellulose with an average diameter of 30 nanometer. Addox was also performed. If you see the addox of the waste, you can see impurities, but the treatment has removed all the impurities and the isolated nanocellulose had only carbon, nitrogen, oxygen as their main compound, and you can see the intensity has gone to 50%. So it says that the nanocellulose was isolated without any impurities. FTRI was performed and it also confirmed the functional group of cellulose. TGA was done. Here also you can see that the raw material 50% weight was lost in 364, whereas isolated nanocellulose 50% of weight loss occurred at 390 degree. So it says that the isolated nanocellulose is thermally stable when compared to the raw material. XRD result, if you see, you can see in embroidery backing paper waste there is less peak. But as the treatment goes, the peak increases and the isolated nanocellulose shows a sharper peak and a higher peak. So it shows that the crystallinity index of the nanocellulose is there and the isolated nanocellulose showed a crystallinity of 87.17% and the crystalline size was 38.33%. So with all the results in my hand, I can conclude that I was able to isolate nanocellulose from embroidery backing paper waste and the physical chemical characteristics proved that it can be used as a reinforcement agent in the production of nanocomposites. So sustainable utilization of embroidery backing paper waste is possible. We can reduce this waste and we can reduce the environmental pollution. So I conclude my talk here. Thank you for your valuable time.
Thank you, Devi, for your presentation. Next, we have Aparna Unnikrishnan to present.
right side is next slide and this is the previous
Okay,
slide.
thank you. It has excellent chemical stability, good mechanical properties and low friction coefficient, and as well as high surface area, optical absorption and semiconducting properties. The other material is activated carbon. It's high porosity and surface area, excellent for absorption and energy storage application, good electrical conductivity, and enhancing stability. So when we combine these materials, there is a nanocomposite, so molybdenum disulfide with activated carbon. So it has high surface area, electrical conductivity and mechanical properties. And it can be used for many energy storage applications. So the method I have adopted here is the microwave assisted method. Microwave assisted synthesis has quite good quality, that is a rapid and efficient method. It uses microwave radiation to heat materials uniformly, shorter time reactions and reduced energy consumption. Usually when we use the normal method like hydrothermal method or co-precipitation method, we need minimum some hours for the preparation of the nanomaterial. So in this case of microwave assisted method, we just need only 10 or 15 minutes for the preparation of the nanomaterial. So the material is an experimental method. So we have been using 0.36 gram of sodium molybdate dihydrate as the molybdenum precursor, and 1 gram of thiacetamide, 1 gram of oxalic acid, 1 gram of ammonium ferrous sulfate. For the homogeneous solution of this material, we have to expose for microwave radiation at 420 volt for 10 minutes or 15 minutes at 160 degrees Celsius, and that's all. The preparation is over. Then we need to centrifuge it and dry it for overnight. For the preparation of the nanocomposite, after this homogeneous solutions, we need to add 0.2 gram of activated carbon. So, and the same process like 420 volt of microwave radiation for 15 minutes at 160 degrees Celsius. So this is the method. And the characterization method, that is Fourier transform, XRD diffraction, FESM, and it acts. So this is the FTIR of MOS2 as well as MOS2AC. For pure MOS2, the absorption peak are observed at 717, 1110, 1337 and 1624. So these are the bands. MO double bond S functional group at 717 as well as 1337. CH bone at 1110 and 161. It is due to the stretching vibration of the OH group. So these are the details of the FTR spectra. Then next goes to the XRD. This is the XRD spectrum for molybdenum disulfide as well as the composite. XRD pattern for MOS2 reveal the peak at 002, 18.47, 29.39, 34.3 as well as 38.9 corresponding to the HKL plane at 002, 004, 102 and 103 respectively. For MOS2 AC nanocomposite, the broad peaks at 23.6 as well as 43.7. It shows the lattice plane as 002 as well as 101. So the crystalline nature we have found, and the crystalline size is calculated by the equation, and it is found to be 9 nanometer as well as 7 nanometer for pure MOS2 as well as molybdenum disulfide AC nanocomposite. So this is the FESM image. The first one shows the pure molybdenum disulfide in microwave method. so small spheres, and the second is for the composite. Smaller spheres are homogeneously spread over the spherical shaped activated carbon. This is the EDAC spectrum. The first is the molybdenum disulfide and next is the composite. So first shows the preparation of the pure molybdenum disulfide with the material molybdenum and sulfur without any impurities, and the second one shows the addition of carbon because since it's a composite. So, conclusion. So we have prepared molybdenum disulfide as well as activated carbon with the microwave assisted method, and as I said earlier, it is the easiest method we can adapt. The prepared nanocomposites are characterized by different techniques, HexRD, FDR, FSM and EDAX. So we can use this prepared nanocomposite for energy storage application, as I said before, like dye synthesized solar cell as a counter electrode or like water splitting, whatever it is. Thank you.
Thank you, Aparna. Thank you all our oral presentation participants for your insightful presentation. Now we would like to invite everyone for a quick photo session with our esteemed speaker. Firstly, I request participants from outside and staff members to assemble near the stage.